Hi, this is Shelley Physics Introduction to Kinematics, which is the study of motion. When things move, they change position. Otherwise, there's no motion. So in physics, we always call position, think like a pirate. The most basic position letter is X. And that's a symbol we'll use. Think like X marks the spot, as a pirate would think on a treasure map. And so X is position. Now there are different kinds of positions we're going to run into. There might be X refers to a horizontal position. If there's a tracking of events, position 1, 2, and 3 along the x-axis. Sometimes you might see a Y representing position, or even an R representing a position away from the center of a circle. So X generally is what we're going to start with. In a race, generally we're moving horizontally. So position describes where an object is. Where is an object? What's its location? Okay, so what's its location? That's the X. All right, there's not really a unit for it because we're not measuring it, but it might be a distance from. So that's where we're going to go next. There's not really a unit here. I just want to introduce that symbol X as position. Now, if you change a position, now we're moving. Now we can study motion. Now, a position could also be at rest. So there is no change in position. The motion could be at rest. But when there is motion, there's a change in position. And that'd be kind of awkward to say over and over again. So if we want to measure the change in position, instead of calling it a change in position, what can we call it? We call it distance. What's the distance traveled by an object? Distance. All right, so this is a change in X. Now I'm going to put a couple of bars around here because this is a magnitude, really. How far is what this is describing? How far did something move? What is the distance traveled? Okay, so how far did an object move? And the SI units for that is M for meters. All right. Now notice distance, this doesn't really have a direction to it. So I might ask, how far away is your house from school? And you might say 2 miles. But I could also ask, where is your house in reference to the school? You see, I'm asking for a location with a starting point. So there's not just a distance involved. Well, my house is 2 miles to the west of the school. And that answers a slightly different question, where? So what quantity would answer where is an object? And that is displacement. Where did an object go? If I'm going to displace my vehicle from the school to your house, or my house, wherever that house is, then we need to know where, what direction also. So here, this is a completely change in position, which includes a direction. All right, so displacement is a distance and a direction. Now, if you've been following the last few episodes leading up to this point, we've been talking a little about vectors. So you might take a note in the back of your mind, hey, direction, that's involved with a vector. So displacement is going to be a vector, and I'm going to talk about that shortly. Okay, so that's also measured in meters. But notice you must have a direction if you're defining displacement. All right, what else do we know about motion? Well, cars move, people run in races, they boat, they move a lot of different things in racing styles, and often speed is important to know about motion. What do we know about speed? All right, so speed. Speed, specifically, think about a speedometer on a car. Does it measure direction? No, it's just how fast. So instead of how far, it answers how fast. How fast is an object moving? So speed is a rate of change in position. Okay? We might also call it a rate of change in position. How fast? Now again, I'm going to put some bars around this because a speedometer, whether you're going forward or backwards, think about it, it doesn't tell you what direction you're moving in. add a compass to it, maybe you can get something else. But if it's a rate, how quickly does an object cover a distance in a certain amount of time? Distance divided by time, miles per hour we're used to seeing here in America. So North America, I should say. So that is measured in meters per second. That's the rate. Right now there are two kinds of speed which we're going to talk about. There's an average speed and instantaneous speed. So I will come back to this. There's an average speed and an instantaneous also. We'll talk about those shortly. So as you see here, there's a pattern emerging. We went from distance to displacement, which included direction, and we got speed, which is a rate of change of position. And I guess we could actually insert there for distance. It's a change in position, the measure of the change in position, measured in meters. I should have added that before. So what about direction? Is speed and direction, is that a quantity? Yes, it's called velocity. And if you see the pattern emerging here, you'll guess that this is the same as speed, but you may actually have a negative change of position. What if you go backwards? Then you may have a negative velocity. So this velocity is how fast and in what direction. What's your vector, Victor? So, sorry, it's from airplane. Aircraft might have a northerly speed, northern vector. You might hear in a war movie some military folks saying, vector into my position. It's also measured in meters per second. And there are some average and instantaneous forms also. I'll put a little mark there to indicate the same thing. So how fast, what direction? So this does include direction. It's a vector also. And keep in mind, when a car is going too fast, it's called speeding, but it's not called velocitying. So there's different contexts you're going to use these different quantities. But you might note that if you travel at 60 miles per hour north, after an hour, you're going to be in a much different place than you travel 60 miles per hour headed south. So that's when velocity becomes important, is when direction is important also. And finally, we get to a quantity called acceleration. Acceleration. The symbol is A. All right, A for acceleration. I've missed one here. Symbol for velocity is V. Speed, you might put an S down, but speed, we should call it the absolute value, the magnitude of the V vector. Okay. And why don't we go ahead and use that vector notation? V is a vector, A is a vector, X is also a vector. A position from a starting point has a direction to it. Okay, so we'll bring that aspect out here as we're building it up. So acceleration is a vector. What's it answer? You say how quickly, at what rate does the velocity change? So acceleration is a rate of change in velocity by its nature. Okay, and if it's a rate, then it's meters per rate of velocity change, then it's meters per second divided by seconds. So you never want to write it like this, but it is meters per second divided by seconds again, and cha-ching, we have meters per second squared. So that is that unit for acceleration that you'll see most often in SI. Now you could go kilometers per hour. That's fine. That is a SI unit, but it's not that base unit, that standard unit. And acceleration also has an average value and a instantaneous value. That's acceleration, short for acceleration. Okay, I was being a little lazy earlier, so I'm just going to go ahead and make a note of this for velocity that it has a average and an instantaneous. I'll shorten that also. So keep in mind there's these averages and instantaneouses. And I'm going to draw that out now. I think it's time to do that. What would the difference between an average velocity and an instantaneous velocity be? Well, here's the example. If we're taking that example of going to someone's house from school, what about that car ride? Well, you might leave your house headed to school, and you pull out of your driveway going about 25 miles per hour around the neighborhood. And once you hit the more local area out of the neighborhood, you might kick it up to 30 or 35 miles per hour. Maybe you take a short highway that gets up to 55 miles per hour, but then you start pulling off and you get closer to school. It's a school zone, so now you're down to 15 miles per hour. And wait, along the way you probably hit some stop signs where you come to a complete stop. You might be speeding up and slowing down for periods of time. Maybe you got to stop to wait for the cars to pull into the school because there's a long line at the beginning of school. It's kind of awkward because we are in this virtual school setting right now, so we don't really have to deal with that kind of stuff anymore, but hopefully we'll have to deal with that soon. Getting back to it, your instantaneous velocity might change throughout the trip. The reading on your speedometer, that instantaneous speed, it might go from 25 up to 35, then you hit a stoplight, you're 0. You might speed up on the next road going 40. You approach the school and you got to slow down to 15. You stop for a car, you make a turn into the school, and finally come to a stop. So your instantaneous velocities are changing all the time. But what if it takes you 5 minutes to go that 2 miles? Right? Then your average velocity would be 2 miles divided by 5 minutes. Okay, so what is that? 4/10 of a mile per minute. Now you might be able to do the math. 60 miles per hour is a mile per minute. But you see there's an average speed that you're not always traveling at. 30 miles per hour would be we'd probably be averaging around 25 or so, 25 miles per hour as our average speed, even though our instantaneous speeds change all the time throughout the trip. So when you're looking at average speed, we take delta x, or average velocity, I should say, delta x over delta t. It's a large change. So even though your positions might be changing quite a bit, actually I should, why don't we go back to this? Even though your velocities might be changing, speeding up from 0, might take a constant, you slow down, and maybe you arrive at school. All right, so the velocity is changing this whole time. And if we're to look at, let's say, the average velocity from this point in time to this point in time, the average velocity would actually be be related to this straight line here, a rise divided by run, a delta v divided by delta t. Okay, so this would be representative, the slope here would be representative of the average velocity. But what about the instantaneous velocity on that trip? Instantaneous velocity would be talking about a very small change, maybe from here to here. What's the speed right along that little segment? Or what's the instantaneous velocity right here? It's 0. This is a 0 slope. Pardon me. The acceleration would be 0 right there, but the velocity would be constant. I'm thinking about the wrong graph here. That's for another lesson. So velocities they are going to be 0 at the bottom. They would increase and become constant at the top, decrease and become constant at this point, and your vehicle might stop right down here at the end. All right, so there's different instantaneous velocities along the way there. All right, so what would an instantaneous velocity be? It would be like, what is the velocity here? Maybe this is 5 miles per hour. This is 10 miles per hour. We're talking about a slow car here. But on a position time graph, going to school may look something like this. Right? All right. So you end up at school this far away, wherever school is. It's at a position, and you get there about at this time. Okay. We'll say the time that you get there. Get there time. All right. Why don't we zoom in a little bit? Okay. Frame it. It's the time that you get there. All right, on this graph here, if we compare what the average velocity means, I got a little ahead of myself with this velocity graph before, but you'll notice it's a delta x over delta t. Position is x. Time is t. So when have you seen an expression like this in algebra? It's when you're talking about slope. So you'll notice that the velocity is related to slope. If we can look at a constant slope here, that means that the velocity is constant along that point in that increment. So from there to there, the velocity is constant because it's a nice straight slope. Let me get another color here. So if we mark this as 0.1 and this is 0.2 and take a rise divided by run, what the rising axis is a change in position, and the running axis is time. This is a change in time. So the average velocity would be for a big segment here, a delta x over delta t, right? But what about an instantaneous velocity? To get an instantaneous velocity, it's still a rate, it's the rate of change of position, but it would have to be like a smaller change, because in an instant, the velocity might change from a slope like this to a slope like this. Well, if we look at these small little changes here, minute changes, you'll see that this velocity is going to be greater than the beginning velocity when it's starting out. So this is a period where you see the line curve here. This is a period of acceleration when the car is speeding up. It's getting faster here. So to really get to an instantaneous velocity, we need to actually zoom in even more. And if you zoom in more, you gotta get the right graph here, and you take a tiny, tiny little segment, there is an associated change in x and change in t, but it's infinitesimally small, and we're going to call that a dx dt. Now zooming back out, what's that look like if we zoom back out? Okay, it's a tiny, tiny little segment here. So an instantaneous velocity is written in a relationship from calculus. It's a rate of change, and position would be the time derivative of the position function. All right, time derivative of the position function. So let's say that if this little segment here is a quadratic, then the position function, x of t, might look like something like, well, the velocity looks like it starts at 0. So it might start at 0. And now let's make this kind of easy. Let's call it plus 2t squared. It would have to be a quadratic in order to have that kind of curve to it. All right, so that means that the velocity function would have to be dx dt, the derivative, the time derivative of that. And that would be 2 stays up front, that's our coefficient, and derivative t squared is 2t. So 2 times 2t would be 4t. So look at what we can do now. At any time during that initial moment of acceleration, right here, if we have a function that fits it, we can plug in any time increment along that little time interval and figure out the velocity. At time of a half second, we're moving at 2 miles per hour. At 1 second, we're moving at 4 miles per hour. At 2 seconds, we're moving at 8 miles per hour. You see how that's going to work. It gets faster and faster and faster. So that's our example of average versus instantaneous velocity. And acceleration works the same way. Average acceleration is a delta v over delta t. And here, let's say if we're looking at a graph of velocity and time, like we have up here, if you see something like this, and we'll do that. How about this? We'll mix it up a little bit. Then we could look at this first segment and notice that the velocity is changing, the slope's constant though, and the acceleration describes a change in v over a change in t. So that slope is the acceleration. The slope of a velocity time graph is the acceleration. All right, but what if this curve, instead of a straight line, what if it were a curved line? That might be a little more difficult. We might ask, what's the acceleration rate right at that moment? Well, if that's the case, then you're looking for an instantaneous acceleration, which would be at dv dt. Okay, so this is where it's breaking out. We're getting a little calculus into this. We can see that the acceleration is the time rate of velocity, so it's the slope of a velocity function. We can see that instantaneous velocity is the slope of a position function. And guess what? You could also have an acceleration graph if you really wanted to. But we're going to stick to these two in the bounds of this discussion. Finally, there's one more aspect to motion that we're going to take a look at, and that's the vector nature. So we've got quantities that we listed so far, and I'm just going to check mark, is it a scalar or a vector? Make a little chart here. Okay, I guess we could have added this, our first chart. If you're making your own, go for it. Let me try that line again. All right, so our quantities again, we've got position, got distance, displacement. A little repetition is good for the brain. And what are the last three? Speed, velocity, and acceleration. Now let's not forget one more quantity here that's sort of been an underlier in all this, and that's time. So let's define time as a scalar or a vector here. First off, position. Where is an object located, or in what position? Now there's no direction from anywhere, so position might just be a scalar. It's right there, or it might be a length or distance from somewhere. Position, I guess that would inherently define that it's got to be someplace compared to another. So you might say it is a vector. How far, what direction is something located? Okay, where is it located? All right, so that might be a vector if you consider that. But keep in mind, position, if you just have an X, it's not describing anything moving at all. It's just a starting point. All right, a starting point. So position could be negative, it could be positive, it could be zero. Negative would be like behind a starting line, positive might be in front. If you ever heard what that quintessential physics problem, two trains are traveling on a train track. One leaves New York at the other at this time, the other leaves DC at this time. Where do they meet? Well, one would have a starting position of 0, the other one would have a starting position of a couple hundred miles away, up in New York City or down in Washington DC, depending on where you're starting. So what next one? What is distance? Remember, that answer is how far. So distance is just a scalar. It has no direction. Displacement is distance and direction. So by that definition, it is a vector. Speed, like speedometer, how fast does something move? That doesn't have a direction. Velocity, remember it can be fast or slow, but also in what direction? So that is a vector. And acceleration is a rate of change in velocity. So there can be positive accelerations and negative accelerations, showing to speed up or slow down. So that shows the direction of change in the velocity. So that is a vector as well. And how about time? Can time go forward or backwards? Sometimes if you're thinking about movies, you think a little bit about Marvel's Avengers or something like that, and you're going back in time, back and forth. You might get a sense that there's direction, but there's not. Can time go north, south, east, or west? Can it go in, out, up, or down? No. So we just usually, in our brains, we think of forward and backwards. There are some people who think of the future as behind them because they haven't seen it yet, and the past is in front of them because that's what they've seen before. In Western culture, we usually think of past as behind us and future is in front of us because that's where we're walking. So there's be careful considering time having direction. If I ask you what time it is, you don't say, well, it's 12:30 to the left. So therefore, time is a scalar. When you multiply anything by times or time squared, you're not changing its vector outcome. Okay. So there's some quantities. Later on, we will talk a little bit about mass and force and things like that. And mass will be a scalar, force has direction, so it's a vector. So there's just a few more to put in the stockpile. All right, so this ends part 1 of Introduction to Kinematics, the study of motion. This should get you started. And then the next segment, if you watch that one, we'll see some applications, both graphical applications and some equation applications. Hope this has been helpful.